The difference in capitalization between VA and VA indicates two different units of measurement. VA, or volt-amperes, represents the apparent power in an alternating current circuit, which is the product of voltage and current. It is a measure of the total power delivered by the source. In contrast, VA, or volt-amperes, represents the average power in an alternating current circuit, which is the product of voltage, current, and power factor. It is a measure of the actual power consumed by the load. In the context of the provided excerpt from National Electrical Code 830.15, power limitation, specified at 250 volt-amps max, refers to the maximum apparent power that the coax cable can handle without exceeding its current carrying capacity. This limitation is determined by the physical characteristics of the cable, such as its conductor size and insulation thickness. Max power rating, specified at 100 volt-amperes, refers to the maximum average power that can be transmitted through the coax cable without causing excessive signal loss. This rating is determined by the electrical properties of the cable, such as its capacitance and inductance. In general, the power limitation is higher than the max power rating because the apparent power includes the reactive power, which is due to inductance and capacitance. This reactive power does not contribute to actual power consumption. Therefore, the coax cable can handle a higher apparent power in volt-amps than it can deliver in actual power in volt-amperes. To elaborate further, consider the concept of power factor. Power factor is the ratio of real power, measured in watts, to apparent power, measured in volt-amps. It represents the efficiency with which electrical power is used. A power factor of 1 indicates that all the apparent power is being used to perform work, while a power factor less than 1 indicates that some of the apparent power is being wasted due to reactive loads. Inductive loads, such as motors and transformers, cause the current to lag behind the voltage, resulting in a lagging power factor. Capacitive loads, such as capacitors and lawn cables, cause the current to lead the voltage, resulting in a leading power factor. In a typical alternating current circuit, there will be both inductive and capacitive loads, resulting in a power factor between 0 and 1. The lower the power factor, the more apparent power is required to deliver a given amount of real power. In the case of coax cables, the capacitance and inductance of the cable can cause a significant amount of reactive power, especially at high frequencies. This means that the apparent power in volt-amps can be much higher than the real power in watts. The power limitation of 250 volt-amps max is based on the maximum current that the cable can safely carry without overheating. This current is determined by the conductor size and insulation thickness of the cable. The max power rating of 100 volt-amperes is based on the maximum power that can be transmitted through the cable without causing excessive signal loss. This loss is due to the resistance, capacitance, and inductance of the cable. The signal loss is proportional to the square of the current. Therefore, even though the cable can handle a higher apparent power, it is limited to a lower average power to prevent excessive signal loss. To better understand the relationship between apparent power, real power, and reactive power, consider the power triangle. The power triangle is a graphical representation of these three quantities. The apparent power is represented by the hypotenuse of the triangle, the real power is represented by the adjacent side, and the reactive power is represented by the opposite side. The angle between the apparent power and the real power is the power factor angle. The cosine of the power factor angle is the power factor. The sine of the power factor angle is the reactive factor. The Pythagorean theorem can be used to calculate the relationship between the three quantities apparent power squared equals real power squared plus reactive power squared. In the context of coax cables, the reactive power is due to the capacitance and inductance of the cable. The real power is the power that is actually consumed by the load. The apparent power is the total power that is delivered by the source. The max power rating is based on the real power that can be transmitted through the cable without causing excessive signal loss. The power limitation is based on the apparent power that the cable can handle without exceeding its current carrying capacity. Therefore, the power limitation is typically higher than the max power rating. To further clarify, let's consider some examples. Example 1. A Coax cable has a power limitation of 250 volt-amps and a max power rating of 100 volt-amperes. The cable is connected to a load that consumes 50 watts of real power. The power factor of the load is 0.5. The apparent power drawn by the load is 50 watts divided by 0.5, which equals 100 volt-amps. The reactive power is the square root of 100 volt-amps squared minus 50 watts squared, which equals 86.6 volt-amps reactive. Since the apparent power is less than the power limitation and the real power is less than the max power rating, the cable is operating within its safe limits. Example 2. A Coax cable has a power limitation of 250 volt-amps and a max power rating of 100 volt-amperes. The cable is connected to a load that consumes 150 watts of real power. The power factor of the load is 0.8. The apparent power drawn by the load is 150 watts divided by 0.8, which equals 187.5 volt-amps. The reactive power is the square root of 187.5 volt-amps squared minus 150 watts squared, which equals 112.5 volt-amps reactive. Since the apparent power is less than the power limitation but the real power exceeds the max power rating, the cable is operating outside its safe limits and excessive signal loss may occur. Example 3. A Coax cable has a power limitation of 250 volt-amps and a max power rating of 100 volt-amperes. The cable is connected to a load that consumes 50 watts of real power. The power factor of the load is 0.2. The apparent power drawn by the load is 50 watts divided by 0.2, which equals 250 volt-amps. The reactive power is the square root of 250 volt-amps squared minus 50 watts squared, which equals 244.9 volt-amps reactive. Since the apparent power is equal to the power limitation, but the real power is less than the max power rating, the cable is operating at its maximum current carrying capacity and should not be subjected to higher apparent power. In summary, the power limitation and max power rating of a Coax cable are two different specifications that are based on different factors. The power limitation is based on the maximum current that the cable can safely carry, while the max power rating is based on the maximum power that can be transmitted through the cable without causing excessive signal loss. The power limitation is typically higher than the max power rating because the apparent power includes the reactive power, which does not contribute to actual power consumption. Therefore, it is important to consider both specifications when selecting a Coax cable for a particular application. In addition to the power limitation and max power rating, there are other factors that should be considered when selecting a Coax cable, such as the impedance, attenuation, and shielding effectiveness. The impedance of a Coax cable is typically 50 ohms or 75 ohms. The attenuation is the signal loss per unit length of the cable. The shielding effectiveness is the ability of the cable to prevent electromagnetic interference. These factors should be considered in conjunction with the power limitation and max power rating to ensure that the selected Coax cable is suitable for the intended application. Furthermore, the National Electrical Code, or NEC, provides guidelines for the safe installation and use of Coax cables. It is essential to adhere to these guidelines to prevent electrical hazards and ensure the proper functioning of the cable system. The NEC covers various aspects of Coax cable installations, including grounding, bonding, and overcurrent protection. It also specifies the types of cables that are permitted for different applications. By following the NEC guidelines, installers can ensure that Coax cable systems are installed safely and reliably. In conclusion, understanding the difference between VA and VA, as well as the power limitation and max power rating of Coax cables, is crucial for selecting and installing the appropriate cable for a specific application. Considering other factors such as impedance, attenuation, shielding effectiveness, and adhering to NEC guidelines is equally important for ensuring safe and reliable operation.